turbine industry. What I like to do is take a little bit of time and go down vertically. Is it what actually goes into one of these projects? How do we actually develop a numerical model, and what do we actually do with it to generate a real engineering application out of it? How do we really drive the product? And so I'm going to talk about numerical simulation of film cooling on high pressure turbine blades. So as you might know, the high pressure turbine, its job is to drive the high pressure compressor in a gas turbine engine. It operates in a combustor exhaust stream, which is about 1600 degrees C, plus or minus, and you want to continue to drive that number up for increased performance. And so the issue you run into is that even your single crystal nickel superalloys, they're only good up to about 1150 in terms of their material capabilities. And so you have to use both passive, which is like a thermal barrier coating, they coat the blades with ceramic, or active cooling technologies. And just to give you an idea where we're at, this is an old graph, but a good graph, where you're looking at cooling technology versus turbine inlet temperature. And talking about as that turbine inlet temperature goes up, you can go from a solid blade, like you would see in a low pressure turbine, to a convectively cooled blade, to both forms of active cooling, which is internal convective cooling and film cooling on the external part. And as noted here, you go to advanced cooling when you got to get up to the current modern turbine inlet temperature levels. So, and that's what I want to talk about, is how do we actually develop models for the film cooling of these things? So, film cooling is, the way they go about it is you take your blade and you drill a large number of holes in it. And the concept here is that you want to take cooler air, which you pull off the compressor, and coat the outside of the blade with a layer of cooler air. And that's going to protect it. And so just an example of that. It's shown for a nozzle. The concept is the same for a blade. And so you bring high pressure compressor air in here, which is relatively cool. It's used for internal convective cooling, and then it's bled through these film holes onto the surface of the airfoil. And then there's that as an application in a blade sense. It's in kind of an idea where you want to coat the outside of the blade with this thin layer of cool air. And when you don't get that right, you have oxidation problems. So this is just a leading edge cooled blade, and what you've got is your thermal barrier coating is spalled off at the trailing edge, and that's an over temperature issue. So the way that these things are designed, and probably every airplane you've flown on today has been designed using steady state methods. And what they do, the design methodology, is you take a 2D axisymmetric representation of the flow through the turbine, and you use experimental data for film effectiveness curves, and you map that onto a thermal analysis model, and that's how you design your blade. The issue with that is that you tend to over-design it. And right now, engines are at the performance level where you have to start optimize the amount of cooling air you're pulling off the compressor. Every piece of cooling air that you pull off of the compressor means that much less mass going through the turbine that you can extract work from, and your performance goes down by a similar amount. So cooling these turbine blades is extremely expensive from an SFC point of view. So the current talk is to focus on, well, this is nice in a steady state sense. You have steady state experiments. But what actually happens when you've got two airfoils running close together? And you've got wakes and shocks and all kinds of other interesting aerodynamic features that rattle around in between the two rows. How does that actually affect your film effectiveness? And we'll talk a lot about this as we go forward. So the specific airfoil we're interested in was designed by Honeywell Aerospace. It's a bizjet engine airfoil, and that's the actual airfoil right there. We actually were simulating a test condition. There's a blowdown test facility at Ohio State University where they test these full-scale engine components at full speed, and there's measurements taken off of that which we'll compare to. So what did we set out to do? We wanted to take this completely cooled turbine stage model and run it two different ways. We wanted to run it the old way, which is a steady state analysis, and then we wanted to take that exact same model and turn it on transiently and start to capture the interaction between the vane and the blade. So that's the way we set the model up, because what we want to do is have exact back-to-back influence of what is the unsteadiness. So one of the things that we were interested in as well, when you've got shock waves passing over these chambers that have holes drilled to the outside, one of the effects they call pulsation is that the external flow field can influence what's going on in the internal flow field. So we wanted to look at that as well. So we've got some details of that internal cooling in the blades as well. So this is what our model looked like. So starting from the cross section up here, there was a high pressure vane here. Flow comes from the combustor simulator up here. This is the rotating component, which is these three blades here. And we modeled it with the leading edge impingement chamber in there and all of these film holes. You can see that here in these details. And then we included some of the aft film rows as well. So next step up for us was to generate mesh for this. And this is an example of what the mesh looked like. Again, we had detailed internal chambers for the convective cooling to understand how the external flow field influences the internal. Detailed film holes all the way through, and then details on the external surface of the blade. And just to look at it a different way. So this is the internal passage and the leading edge of the airfoil. These are film holes that are drilled through the surface. And this is the external flow field. So just for reference, these were about 10 million elements in the model, which is fairly small for today's standards. For you guys who are interested in CFD out there, some details on the analysis tools that were used. It was CFX version 11, so this is a few years old, this study is. Second order spatial discretization, first order temporal discretization, and fairly standard modeling for the rest of the components. Two equation turbulence and fairly basic heat transfer modeling. This is a blowdown tunnel, so the test time was about 3 milliseconds or something like that. So really there's no change in the blade metal temperatures during this test. So the things that we wanted to do, we wanted to look at were we capturing the unsteadiness that was actually present in the facility. So we wanted to compare against the measurements. And then we want to start looking at what does the model tell us the impact of this unsteadiness is on the flow conditions and the film effectiveness on the blade itself. So we'll work our way through all of those conclusions. So this is what the model is attempting to simulate. What we're looking at here, we're actually sitting on the blade. We're in the rotating frame of reference here. So we're watching the vane rotate past us here upstream. And these colored streaks here are entropy. So we're looking at wakes coming off of the vane. And this is pretty standard aerodynamics, where that wake comes off, it enters into the blade passage, it gets stretched and mixed out as it goes downstream. So that's just to orient you with what the model is predicting in terms of unsteadiness. So in terms of validation, there were pressure data taken off for both airfoils, both the vane and the blade, for us to compare to. In terms of the vane loading, so this is pressure along the vane surface. On the suction side and on the pressure side, you can see that the model was in good agreement there. Similarly on the blade, we had good agreement with the mean data, which is the symbols here. And the other thing that we were happy with in terms of the agreement was, if you note that the unsteadiness in the measurements here on the blade suction side was matched pretty well by the range of unsteadiness in the analysis. So we thought we were on the right track in terms of capturing the unsteady loadings on the airfoils. We looked at it a little bit differently. We took the signal coming through at the blade leading edge, fast Fourier transform, to process out the frequency content, which is shown here. And so the dark symbols is the CFD analysis, the light symbols is what was actually measured in the test. And what we were looking for is, did we get the amplitude of the unsteadiness right? And we were about 80% or so. The issue is that there are 4 struts, which are fairly far upstream, which were not included in our analysis model, and that count of 4 happens to be right on top of our vane count. So this additional amplitude here was what created the difference we saw here. So at the end of the day, we were very unhappy with what the model was predicting for unsteadiness at the leading edge of the airfoil. Okay, so on to the meat of the matter, which is what's going on with the film cooling. So on the left is the transient analysis, on the right is the steady state analysis, and what we're looking at here is the effectiveness of the film that you're generating on the surface of the airfoil. So you can think of this as 1 over the temperature. So areas that are green or red means you have high cooling effectiveness, which means the blade is going to be well protected by the film. Areas that are blue is very low film effectiveness, and those are the areas that are going to be hot in your thermal analysis. So one of the things to note immediately is that the film was actually very active in the transient calculation. There's a lot of stuff going on up here, which in the steady state analysis, if you were a blade designer and you looked at this steady state analysis, you would say, I've got one problem, which is right up here at the trailing edge, which is a common place to have a problem. But everywhere else, I'm in pretty good shape. You look at the transient analysis, and you'd have maybe a different conclusion for your design. If we turn the blade around and look at the other side, this is now the suction side, the story is not as different here. So on the suction side, where the blowing ratios are a little bit lower, you've got good film generation in the steady state, and you might make the argument that it's okay in the transient analysis as well. When you take those pictures and you time average the transient analysis, that's these pictures over to the left, again, you can see that on the suction side of the airfoil, maybe you're in pretty good shape with a steady state analysis. On the pressure side of the airfoil, there was actually a large difference noted in between the transient and the steady state calculation. So one of the things you'll note here, if you look at the leading edge right up here at the top, in the steady state analysis, you would say, well, maybe I've got a problem here. The reasons you have a problem is in the steady state analysis, that impingement point, leading edge, is in between 2 film rows. And so the film goes to either side, and there's a streak right down the center that's going to get no film, very hot. Transient analysis, you don't see that because as the wake washes over, those film rolls get pushed in opposite directions, and it smooths out that film coverage. This is actually in line with what you see with actual engine operation. Very rarely do you have leading edge issues due to poor film coverage. So again, that was more information that said that our model is heading in the right direction. So this is probably going to be a complicated chart to explain, but what we want to do is then convert the information from the analysis back to a form that a designer could use. And that's these curves here. So the black line is the steady state analysis. And what you want to have is a certain level of effectiveness to protect your blade. So the effectiveness is really how thick that layer of cool air you're building up on top of your airfoil surface is to protect it from the hot air coming out of the combustor. So if you'll note, there's a major difference between what the steady state is saying and what the transient analysis is saying. So there was the important finding of the study was that we were not predicting the proper thermal response with a steady state model. So the question is, why is this? And so there's a method that's been published previously and experimentally shown. These are actually experimental pictures that are shown down here, where if you take and post-process your results to look at what they call a perturbation velocity, which is really you really subtract off the mean velocity field, you can get these things that are called negative jets. So this is actually the weight coming off of the upstream airfoil. And you can see that negative jet actually impinges on the suction surface of the airfoil. So when we saw this, we looked at this and thought, you know, I wonder if that's what's happening on our blade, on the pressure side. So we went and looked at these perturbation velocities. So it's plotted 2 different ways, one with just vectors here, and one with those vectors overlaid on top of the wake plot that we looked at earlier. And what you can see is in the wakes, see how these vectors are streaming towards the suction side? Very similar to what we saw in the experimental visualization chart. And so I think we are actually seeing these strong negative jets influence the flow field. So, and in a steady state analysis, you don't get any of this because all you have is the mean flow field. And so this is just one snapshot in time here, where we were looking at very low film effectiveness on the pressure side of the airfoil. So the question is, well, what's causing that? So we've got these negative jets that set up in here. That's these dashed lines. What we found is that actually there's a counterflow flow that's introduced because of these negative jets. In the experiment, the jets were very widely spaced. In a modern gas turbine like this, those wakes can be very closely spaced. And when you do that, you generate a counterflow. So you can see these perturbation velocities are running upstream right here. That's the mechanism that was causing that reduction of film effectiveness we were seeing in the model. And so this was a very interesting finding, and now we're looking at, well, what can we do to mitigate this? And that's part of the ongoing work that's continuing today. But that was just an example of how we would take a simulation, work its way through an engineering process to find out why are we having issues with our fielded blades. And we actually showed those results to a service engineer, and he said that's exactly where we're having problems, is at the area that we were showing the low film effectiveness. So that's the conclusion of my talk. I'm happy to answer any questions.
Any questions?
The mixing loss for the airfoil?
There was direction, right? So were you able to analyze if there was any increase in the pressure over there?
Yeah, we didn't look at the mixing loss with the unsteadiness at this point in time. So it was not something we were interested in at that. This is a purely for heat transfer. We weren't looking at aerodynamic performance at this point in time.
Okay, thank you.
Once you complete this analysis, are you looking at transferring these facilities to the structural side? With the CFD analysis?
The CFD analysis
So
part.
you're not looking at the thermal part and the structural side of.
These results will be mapped on to a full blade thermal analysis, and then from there you go into the creep calculation mechanically. So they would be used in that way.
Right. And because like one way of looking at it is like it's a pretty good analysis at what I've seen, and transferring this transient data onto the thermal analysis, in particularly the results that you have shown comparing the transient results with the steady state analysis, and then transferring the actual transient data to the mechanical analysis will give a pretty good insight into how the thermal behavior, how the thermal structure will behave.
Yeah. Historically, we've looked at this and said that the frequency of the unsteadiness we're seeing there is so much higher in the Aero work that the structural response time is much slower, and it's not going to see this effect. But we're actually actively exploring how do you connect the Aero and mechanical transient response. Maybe not for this level of detail, but maybe in larger scale things, like for instance in cycle changes. As you're ramping up or ramping back down, we're looking at how do you couple the CFD and the mechanical analysis.
Thanks.
When you said you have done the transient analysis and you know that in the CFX you have taken only first order and time step. So first order and time step would actually nullify the transient time. So you can't actually capture the time with an accurate sense. It's only first order. You see, in time you are looking at a truncation which is very high. The truncation error in time is very high. Did you do any kind of in one slide I saw that says pseudo time stepping you have done.
That's only for the steady state.
Pseudo time stepping is only for steady state.
Right.
So you mean to say that between the transients you are going for steady state in that time step, or like what is that? What does that mean?
The pseudo time stepping is that's how CFX integrates the flow solver forward.
Yeah, but so when you say pseudo time step, say suppose your time is about 3 milliseconds or something, over which you said.
That was the test time. That was the test time.
That means your CFX, what are the CFD predictions should be of that time only. You're looking at.
Okay. There's a lot of answers to that question. So there were three questions there. First is it first order in time? We were just looking to look at trends. We had no idea what we were going to find when we started out in this case. So before we go do the really complex calculations with the higher order methods, we thought, let's go look at it, just see what we get first order. And then the pseudo time stepping is only for steady state time integration. That's one of the methods that you can use in CFX to get to a steady state solution. And we were really looking at modeling a steady state operation of that 3 millisecond window. So we weren't really looking to model that 3 millisecond window in the test. We were just assuming that it got up, it ran at the test was 150 milliseconds, but they get up and they say, okay, this 3 millisecond window is the test point. And so that's what we were modeling. We really didn't use the 3 milliseconds for anything in the calculation.
And one more thing, the amount of grid cells which you have used, it's about of millions, 2.5 million cells.
It was about 10 million total for that.
Yeah, 10 million. That means you are effectively solving a direct numerical simulation. Then why do you need a turbulence model over there?
It would need a lot more than that for
If you would have improved the time step accurately, and with that kind of grid, the DNS simulation would give or LES simulation would give a better approximation when compared to the turbulence model which you are using over there.
I agree, but I do think the model would have to be a lot larger for an LES simulation. I would like to go back and brick it rather than using TETs. And again, we were just looking for, we were exploring. The question was why is our part burning up on the pressure side when your steady state model tells you that it's well film cool on the pressure side? So that we were just looking at this point in time.